in a good transmission line, one conductor must be ground. From the source of energy to the load, this conductor must be unbroken. Next to that conductor must be the unbroken dielectric, because that's where the field moves. Then you have the switched conductor that you use to add or remove the transmission lines or spaces where you want the energy to go. The amount of energy that can move through these spaces is determined by the three-dimensional geometry of the space and the dielectric material. Every time this geometry changes, there will be a reflection point. These discontinuities are important to understand. We have to know what the behavior is going to be based on the geometry of the transmission lines that we've created, and understand how effective they can be in allowing the energy to move, meaning their capacity. It's like if you have a hose that's 1 gallon per minute and you need 5 gallons per minute, you're not going to get it from that hose. You're going to need 5 hoses, or you're going to need a bigger hose. And that's the problem we haven't been solving. We haven't been getting a bigger hose or more hoses. We've been changing the material of the hose in the hopes that we can force more water through that. But it doesn't work that way in electronics. Plus, we've really got to understand how long it takes to move this energy. You've got a capacitor on one side of the board, and you've got an IC on the other side of the board, and you need to move that energy without causing radiated emissions events. How do you do that? It's by understanding the behavior of the waves and how you can partition the power supply so that it will not present these extremely fast switching events that are caused by the IC to be applied to a length of conductor that will allow it to start radiating. Transmission lines are the same whether it's power or a logic signal. When you turn on a logic switch so that you're driving an address line or a data line, at that point in time, it's a power supply. You've added a space, and energy is going to flow into this space. It's no different than bringing energy into the IC. It gets to the chip, and then we have this switch array that add or subtract spaces that then redistributes the energy. So an IC is just a power distribution channel. It's a switch array that adds spaces that you let the energy flow into. And again, when you first turn on a switch, the field doesn't have a clue what's at the other end. All it knows is this is empty. I'm going to let everything I have go into this space based on the capacity of the sourcing transmission line. It thinks it's a short circuit because it's going to consume everything. And until it gets to the other end and reflects, the fields that are coming into this space have no idea what's going on, and they're just going to continue to flow into the space. We need to understand this. And the energy will not go back into the driver. It always goes forward. So that's the good thing about power distribution systems, is the water moves forward, just like it doesn't go from the lake up to the top of the mountain. The same thing with power supplies driving into the system. It doesn't go back into the power supply. It gets redistributed and consumed as it moves farther and farther away from the switch, from the source of the energy.